so let's get into talking about the electrochemical driving force. Okay, we talked about the electrical driving force, we talked about the chemical driving force, and today we're going to talk about putting them together. Now, we want to just sort of jump back and remind ourselves why we're even talking about this. So we're talking about the forces that are acting on a particle across a membrane, right? And so we talked about the two forces separate, but we want to understand that in actuality, in the body, both forces are acting simultaneously. So we have to decipher what the total sum of those forces will be on a particle. And if those forces are acting in different direction, we have to decipher what is the overall net direction of that force. What direction will that particle move in? Will it move into the cell or out of the cell? So in putting those two forces together, we have to figure out which of those is the more influential force on the net movement of these particles, okay? Let's look at a first scenario, which is pretty easy, pretty straightforward. And this is if the chemical and the electrical driving force are acting in the same direction. And if that is the case, the electrochemical driving force, right, putting those two forces together will very obviously be in that same direction. And in order to get the magnitude, the strength of that driving force, we simply add the total of the two forces. So this is the sort of easy scenario. If the forces are in the same direction, the sum of the two forces, you just add them together, and that net direction is the direction of the electrochemical driving force. All right? Now, if the chemical and electrical forces are in opposite directions, we have to decipher which of the forces is stronger, which of the forces is influential, more influential in terms of determining the overall electrochemical driving force. And then the magnitude will simply be the larger force, and we subtract the smaller force from that. So I'll say that again. If the forces are in opposite directions, right? We had a chemical driving force that's moving a particle out of the cell, and we have an electrical driving force that wants to move a particle into the cell. So the forces are in opposite directions. Here, we must decipher which force is more influential, is more dominant, is stronger. And for that, we have to consider the equilibrium potential, which we'll talk about in a minute, okay? Let's look at a question here. If a chemical gradient existed, under which conditions would a particle not be transported across a membrane, even if the membrane is permeable to that particle? So if we had a gradient, if we had a concentration gradient, under what condition would there be no movement of that particle, even in the case where the membrane is permeable to that particle? Question or answer?
If the force of the charge is
that's true, that's correct. So if I get what you're saying, if the force, the charge on the particle, right, the electrical force, is just as strong, but in the opposite direction of the concentration gradient. All right, so that basically means we have two forces that are just as strong, right? They're equal, but they're in opposite directions. They'll cancel each other out, and we'll have no net movement. All right, does that make sense? And that's sort of what's happening at equilibrium. That's what we're going to talk about next, the equilibrium potential. Mm-hmm. So they're going in opposite directions, right? We had an electrical force moving a particle out of the cell. We have a chemical force just as strong, equal, moving a particle into the cell. They'll cancel each other out, and that particle will go nowhere, right? No net movement. And that's what happens for an ion that is at equilibrium. Okay, that's what the equilibrium potential is. All right, so let's talk about the equilibrium potential. This is a type of membrane potential that exists when the electrical force is equal to, but opposite, of the chemical force. And when we think about the equilibrium potential, we're really talking about the concentration gradient. All right, we talked about the concentration gradient. This is that scenario where you have a high concentration of an ion, whatever the ion in question is, on one side of the membrane, and a low concentration of that same ion on the other side of the membrane. And so we have this force where these particles want to be at equilibrium. They want to start dissociating until there's an even number of particles of solutes on either side of the membrane, right? And so the chemical driving force, the concentration gradient, is what determines the equilibrium potential. Whereas the electrical driving force, which is a charge on the particle, is what determines the membrane potential. Okay, I'll say that again. The equilibrium potential is determined by the concentration gradient, right? This is the force that's acting on these particles that want to dissociate to be at equilibrium. And now, when we talk about being at equilibrium, right, the membrane potential is the same as the equilibrium potential, right? The forces are in equal and opposite direction. Alrighty? And so when we talk about membrane potential, we usually use this symbol here to represent that, E subscript X. And we speak about equilibrium potential relative to a specific ion. So the equilibrium potential for potassium will be where there's no net movement of potassium across the membrane, right? The forces acting on potassium are equal and opposite. The concentration gradient is creating a force in one way. The electrical driving force based upon the charge of potassium is creating a force in the opposite direction. And so at this membrane potential, at this stage, there's no net movement of potassium. Potassium is at equilibrium. Okay, and so in this case, the subscript would be a K for potassium, right? That K plus would be potassium, right? And this illustration sort of highlights that. What we can see here is that the equilibrium potential of potassium is negative 94 millivolts, right? The membrane potential of potassium is also negative 94 millivolts. What this means to us is that the chemical driving force, right? We said the chemical driving force determines the equilibrium potential. The electrical driving force determines the membrane potential. And so that basically means that the chemical driving force and the electrical driving force are equal and opposite. All right, I hope that's making sense. Let me know if it doesn't. Any questions on that? Okay, so let's look at how we determine the direction. Let's look at a flow chart for determining the direction of the electrochemical driving force. So let's try to synthesize this a little. Okay, so we're determining the electrochemical driving force. All right, so in order to determine the net direction of the ECDF, which is the combine those two forces, we need to identify the direction of those forces individually. So we start by identifying the direction of the chemical driving force and the electrical driving force, okay? And so we sort of have several different scenarios here. We talked about the first one, which is pretty straightforward, and that was if the electrical driving force and the chemical driving force are in the same direction. Right? They're acting in the same direction. That particle is naturally going to move in the direction of both those forces. And so the ECDF, right, combining those forces, moves in that direction. Okay. So this is that first nice, easy scenario. These forces are acting in the same direction. Now, if they're acting in opposite direction, it gets a little bit more complicated. So if the electrochemical or if the electrical driving force and the chemical driving force are in opposite directions, then we have to look at the equilibrium potential and the membrane potential. All right, we look at the equilibrium potential and the membrane potential. So we're going to compare EX versus VM, right? EX being the equilibrium potential and VM being the membrane potential. Now, if the equilibrium potential represents, what force did I say the equilibrium potential represents? What force determines the equilibrium potential? Is it the chemical or the electrical? What's the force that wants particles to be at equilibrium? The chemical force, right? The concentration gradient, that's what determines the equilibrium potential. So the equilibrium potential is indicative of the chemical driving force, whereas the membrane potential is indicative of the electrical driving force. Okay, and so we're going to look at the equilibrium potential and the membrane potential to determine which is stronger, and then the force that is influencing that potential will be the more influential force. Okay, so if we take this into consideration, we then have three scenarios here, right? Let's look at what those three are. If the equilibrium potential is greater than the membrane potential, then which force is stronger? If the equilibrium potential is greater than the membrane potential, which of the forces is stronger? The chemical driving force or the electrical driving force? So if the equilibrium potential is stronger than the membrane potential, which of those underlying forces is more dominant? The chemical driving force, right? So if EX is greater than VM, right? EX being the equilibrium potential, VM being the membrane potential, then the chemical driving force is greater than the electrical driving force. All right? And which direction do you think the overall electrochemical driving force will be? In the direction of which of these forces? Also the chemical, right? So the ECDF, and just to remind ourselves here, ECDF is combining those two forces, right? We're combining them together and we're trying to see which is more dominant, which direction is more dominant. So the ECDF will follow the chemical driving force, okay? That's our first scenario. Let's look at a second scenario here. If they're equal, so if the equilibrium potential is equal to the membrane potential, then what's the scenario there? We talked about this. They're in opposite directions, as we know to be true, and now they're equal. They're at equilibrium, right? So no net movement, right? So if the equilibrium potential is equal to the membrane potential, then that tells us that the chemical driving force is equal to the electrical driving force, and then that total sum force, the electrochemical driving force, equals 0, right? No net movement here. I'll put equilibrium. So these particles are at equilibrium. Okay? And then our final scenario will be the reverse of this first scenario. This is if the membrane potential is greater than the equilibrium potential. Then what do we think will happen here? Which of our two underlying forces is more dominant, is stronger? The electrical driving force, correct. So if membrane potential is greater than equilibrium potential, then electrical driving force is greater than chemical driving force, and our total electrochemical driving force will follow the direction of, follow the direction of the electrical driving force, right? The more dominant underlying force. Okay? So this is if the chemical driving force wins, and that happens if the equilibrium potential is greater. This is if they're equal and we have no net movement. And then this is if the electrical driving force is greater, and that happens when the membrane potential is larger. Okay? All right. Any questions on this? We're going to look at another scenario that will make this a little bit more clear if it's not clear yet. Okay, any questions here? Okay. So let's look at this scenario here, right? And this is looking at potassium again. So what we can see here is that on the left, we have a scenario where the membrane potential is weaker than the equilibrium potential, or the equilibrium potential is stronger than the membrane potential, okay? Now the forces are in opposite direction, as we can see. And so we're gonna look at the force that's bigger, right? Which of the forces is bigger in terms of looking at the numbers? Which of those forces is bigger? Right, the equilibrium potential of potassium. So the equilibrium potential here is bigger, and so which of the underlying forces is going to be more dominant? If the equilibrium potential is greater than the membrane potential? Is it the electrical driving force or is it the chemical driving force that's more? The chemical driving force, right? The chemical driving force. And so what we see here is the electrochemical driving forces, right? The sum of those two forces is naturally going to go in the direction of the bigger force, which happens to be the chemical driving force. Okay? Let's look at another scenario. If the membrane potential is stronger than the equilibrium potential, and that's what we can see here, right? The membrane potential is negative 100, and now these are absolute values, so it's becoming more negative, meaning that there's a greater magnitude of the force here. Whereas the equilibrium potential is only negative 94. And so because we have a stronger membrane potential, the sum of these two forces is naturally going to go in the direction of the electrical driving force, right? Simply because the membrane potential is greater, it's more influential on those two forces combined. All right, so as you can see here, the electrochemical driving force will go in the direction of the greater force, of the more influential force, which happens to be the electrical driving force in this scenario, okay? And again, to look at the magnitude of the electrochemical driving force, we simply subtract the smaller force or the weaker force from the greater force. So in this first scenario, we subtract the electrical driving force from the chemical driving force. And you can see this arrow is much smaller because that's the magnitude, right? Because they're going in opposite directions. We just subtract them and the magnitude will be a little bit smaller, but the overall direction will be in the direction of the stronger force. Right, very true on this side as well.